everybody. In this video we're going to be looking at sample sizes in confidence intervals. So we looked at building confidence intervals for proportions, means, and standard deviation. And what we saw was our interval involves some amount of error. So our point estimate, for example, for a mean was always the mean of the sample, but then we had plus or minus some amount of error. So my first question here is, how is the error of our interval estimate, or that capital E quantity, how is that E related to the sample size? Well, we have different formulas for this, but most of them involve some sort of n in the denominator. So if we have, for a proportion, for example, this was the square root of p hat q hat over n. We had a similar couple of formulas for means. So this means that if the sample size n gets bigger, right, it's in the denominator, so that error is going to go down. If the sample size gets smaller, then our error will get bigger. And again, this should make sense, because if you have a large sample, then that means we're going to have a better idea of what the population is doing. If we talked to 1 out of every 2 people in the United States, that would be a very, very large sample. We would have a really good idea of what the population parameter was. So a large sample gives a small error. Correspondingly, if your sample is too small, then your error is going to be quite large. So no matter what we're estimating, the bigger the sample size we can get, the better. But in practical terms, it can be very difficult and in fact very costly to get very, very large samples. And for some things that you might want to study, the sample sizes just might not exist. If you're doing, for example, research on HIV treatments in the US, and you have to find people who have HIV, the number of people in the population with HIV is fairly small, so it would be difficult to get a very, very large sample for a study like that. If you do studies that are really involved, like sleep studies or drug studies where people have to be coming in for treatments and there's a lot of cost involved, again, you would want to try and keep your sample as small as you could without affecting your results. So the question here is, how can we make E smaller? We don't want a really large error in our calculation, otherwise our results won't be very helpful. So we want a large sample, but we want to figure out what an upper bound is so that we don't have to get a sample of hundreds of thousands of people every time. So as an example, suppose we want to find out what proportion of a particular county is going to vote for a candidate in some election. And we're using a 95% confidence interval. The confidence level, of course, will affect this process. And we want to know, how big will our sample have to be if we want the error to be less than half of a percentage point. So here we want our error, our margin of error, to be less than 0.005, right? This would be 0.5%. So this means that whatever estimate we get will be plus or minus 0.005 or plus or minus 0.5%. And that's a fairly accurate estimate. So to compute this, we're going to use a formula from the book. And this says that our minimum sample size is given by the n value. In this case, we're estimating a proportion, so we're using the formula for proportions. This is our critical number. This is the same kind of critical number that we were looking at in the confidence intervals. Critical number squared times p hat times q hat over e squared. And the E squared here represents how big we want the error. So in this case, we'll be using the 0.005 for E. Now, everything in this formula is coming directly from the computations that we did for confidence intervals. So there's nothing new here. We're just sort of combining it in a different way. And in fact, this is really coming from the exact same formula, but solved for the variable n instead of for the variable E. Now notice that in this formula we would have to actually already know what p hat and q hat were, which means that we would have had to already take the sample. And a lot of times we don't know what these values are because if we've already taken a sample, we've already found a sample size. So typically we would want to be computing this sample size before we go out and sample the population. So in this case, if we don't already have the p hat q hat, we have a secondary formula where instead of using the p hat and q hat, we put in 0.25. And 0.25 is the very largest possible number that p hat times q hat could be. So we're sort of hedging our bets here so that we get a value that's going to work for us for any values of p and q. So this is the formula we'll use in this case because we don't actually know what proportion of our sample is going to vote for the candidate. We haven't taken the sample yet. So we'll put in our critical number. Now our critical number for a 95% confidence level, this is the same process that we looked at before. You can use the z-score table, and this is one of the special ones that's in the little mini table at the bottom. So this is a critical number of 1.96 times 0.25, or 1/4, divided by, and then here we're using that error value. We wanted our error to be no more than 0.005. So if we put all this in, we're getting a number here, 38416. And this is a sample size, which means this has to be a whole number. So we're always going to round up to the nearest whole number. We always round up because we want to make sure we have enough people. So it's better to add one extra person than to round down and then have your error a little bigger than what we wanted. So this says that in order to get our estimation of the proportion that are going to vote for our candidate within 0.5% or half a percentage point, we'd really have to talk to 38,416 people. Now this is a really large sample, and that's really just because the error that we want is really tiny here. So typically error on a lot of poll type questions is more like 3% error. So we could repeat this with different error values and find out how large of a sample size we would need. So this example was specifically for proportions. There will be other similar formulas for means or standard deviations, and you can just find those in the book. I'm not going to go through them here. They're very much the same kind of process. You will have to be using critical numbers for either the z distribution or the t distribution or the chi-squared distribution, depending upon what you're looking at, but the process is very similar to what we talked about with confidence intervals. So just as a note, for these other similar formulas, you can get those from that pull-out sheet from the textbook. They're nicely organized just all into one little box, and then we can look them up easily there. So to finish up, here's a problem for you to work on. This is also looking at a proportion, so you can use the same formulas that we were looking at in this section. And that's it for this video. Thanks. See you later.